My name is Hado van Hasselt, and today I will be talking to you about off-policy and multi-step learning. And if these intros are starting to sound a little bit repetitive, that's okay, as long as the content of the material is hopefully more engaging to you. In terms of background material, I would advise that you have a look at Sutton and Bartow's chapter 5, 7, and 11. If you forgot anything about those, because you likely looked at these before already. But there will also be some material in this lecture that is not contained in any of those chapters, so just be mindful of that. But we're going to start, before we dive into any new material, in recapping and also motivating what we're going to do today. Just at a very high level, we've seen this over and over again now. The point is to take actions in the world where we observe certain observations which might include some partial information about the environment state, but typically not the full environment state. And we want to figure out how to take actions so to improve our rewards. Where the agent internally might have a policy, as we discussed last lecture in our policy gradients and actor-critic discussions. It might include a value function, which is predictions about the future, also potentially a model or multiple models. And then the general problem involves taking into account time and consequences, because the decisions don't just impact the immediate reward, but also the agent's internal state and potentially the state of the environment, which means certain actions might have long-term consequences, which might also not be immediately observable. Now, in previous lectures, we talked about how to do model-free prediction and control in this setting. We talked about using multi-step updates rather than one-step updates and eligibility traces, because sometimes this provides a better trade-off in the learning efficiency. We also talked about more theoretically about understanding dynamic programming operators, because a lot of reinforcement learning algorithms can be understood as approximating dynamic programming operators. So it's really helpful to understand how these work in principle, because then the algorithms that we actually deploy might be considered approximations of this, and therefore might be better understood if we understand the fundamentals. In addition, we talked about what happens if you then include function approximation and how to do this, and typically we use gradient-based algorithms when we do that. We talked about model-based algorithms a little bit, and algorithms like Dqn. And more recently, we talked about policy gradients and actor-critic algorithms, which, as I said before, keep an explicit representation of the policy and try to update that directly. Now, in this lecture, we're going to talk about off-policy learning, again, because we touched upon this before, but we're going to focus a little bit more on this specific topic because it's important, and then especially when combined with multi-step updates and with function approximation. This will be both in the setting of model-free prediction and control, but also in the setting of policy gradients. We won't be talking about models so much in this lecture. Now, in terms of motivation, why do we care about this topic? Why is this important? So there's a number of reasons, actually. So first off, what is off-policy learning? Well, off-policy learning is learning about a different policy than that is used to generate the data. And there's a number of reasons why you might want to do that, but in general, it means you're basically posing what-if questions, hypothetical, counterfactual what-if questions. What if I would have done this rather than this other thing that I actually did? Now, use cases in which this is useful include you might want to learn about the greedy policy, but you might not want to follow the greedy policy all the time because that doesn't explore sufficiently. Q-learning is an example of an algorithm that does this, and it's often named as a canonical example of an off-policy learning algorithm. And this is true, but this is not the only off-policy learning you could do. In addition, or instead, you could also learn about many other policies. This could be useful because you, for instance, care about these policies, but also because you might just want to learn a lot about the world and condense all of that information into the agent somehow to reuse this later. The greedy policy is typically a tempting thing to approximate because then you can do something like policy iteration, but it doesn't mean it's the most effective thing to only learn about the greedy policy all the time. In addition to that, you might have certain other constraints. For instance, you might want to learn from observed data, for instance, logs that you've stored, or from information gathered from other agents, and learn maybe about the greedy policy there or about a different policy. And this could just be because you're interested in a certain application. Oh, I have this data store, for instance, collected by watching humans interact with the system and seeing which actions the humans took. And you might actually want to then ask what-if questions. What if they have done this other thing? What would have then been the value? Or what would have then been my predictions? And of course, this also includes learning from your own past policies, because that's also just a data store. So you could imagine doing something called replay, where you collect a lot of data, but you keep on changing your policy, right? Because you want to keep on getting better. But that means that the old data that you've collected doesn't actually correspond to your current policy anymore. And then you might want to do off-policy learning from that, because the behavior that generated the old data doesn't match the current behavior that you're interested in. So that might be a different reason to want to do off-policy learning, because you want to do extensive replay, for instance, in order to be very data efficient, because you can then reuse all the data that you've generated so far. Now, there's a different reason why off-policy learning is important, rather than just trying to learn about many things or trying to learn about a greedy policy or something like that in a value-based method. It's also very important in policy gradients to correct for mismatch in data distributions, and I'll go into that a little bit more in a second. So first, let's just remind ourselves what we could do. So if we want to do off-policy learning about any different policy pi, so we're following some policy mu, which is not given on the slide here, but it might be different from the policy pi that we're actually interested in. Now, one thing you could do is you could use this general Q-learning, or sometimes called expected Sarsa update. This is what Rich and Andy call it in the book, which is basically straightforward application of bootstrapping, where we take a certain action A, or we consider taking a certain action AT in a state ST, and then we just see what happens if you take that action. But in the next state, we consider following this policy pi. And pi does not have to match the behavior. It could match the behavior. In that case, you're just doing on-policy expected Sarsa. But pi could, for instance, also be greedy, in which case you're doing Q-learning. But it could also just be something else. So in expected Sarsa, in the original expected Sarsa, it was meant to be the current behavior policy. In the book, expected Sarsa is used to refer to this more general algorithm where it can be anything. In Sarsa, this is also interesting to point out, this still corresponds to this update, but then pi is a stochastic policy, which assigns all probability mass on the action that you actually pick in the next state. That is an on-policy algorithm, but in general, you could just plug in anything there and learn about whatever policy is of interest to you. Okay, so now moving on, this is all recapping things that you've already learned about before. We might want to do multi-step updates, and then we can't use this trick of bootstrapping that we had on the previous slide, because now we have to consider what happens on a longer trajectory. So just bootstrapping is not enough anymore. And then we introduced importance sampling corrections. So basically, if we have a trajectory, tau, which spans from ST to as big T, maybe that's the end of the episode, then we can correct for the distribution that was used to generate this by basically multiplying the observed return G, let me point at it with the mouse, by multiplying this with the probability of generating that trajectory that we saw under the target policy that we're interested in, and dividing that by the probability of that same trajectory under the behavior policy that we're interested in. If we do this, then the expectation of this return will be equal to the expectation of the return that we're interested in under the target policy. So note here that GT is the uncorrected return, and GT with a hat is the corrected return, which is defined over here. And what this is saying is that if you make this correction, and then you take the expectation under the behavior policy mu, then with this correction, you're guaranteed that the expectation of this whole entity here, which we call the G hat, will be equal to the uncorrected return under the target policy. So this provides us a method that allows us to take any return generated under any behavior, and then correct for the distribution of generating that trajectory that led to the return to something that has the right expected value. So let me make that a little bit more concrete. What could happen is you had a trajectory that was actually quite unlikely under your behavior policy, but it just happened to happen. But it's one that would happen all the time under your target policy. Now what would happen here is that effectively then you'd have a number that is relatively high divided by a number that is relatively low. So we would upweight that return. And that makes sense because this return would be more common, this trajectory, under the target policy. Conversely, we could also, of course, and this might be the more common case, we could generate a trajectory under the behavior that is quite likely to happen, but would be very unlikely under the target policy. Maybe it's even impossible. Maybe the probability of that trajectory, which just happened under your behavior policy, would literally be impossible under the target policy and the probability could be 0. In that case, we just zero out that return, or we downweigh it if the probability is not quite 0 but very low. And this means that we're basically reweighting the samples in exactly such a way that in the end the expectation is the same to the thing that we actually want. Now additionally, as shown on the slide, the probability of a trajectory under a policy divided by the probability of that same trajectory under a different policy can actually be written down as just the multiplication of the individual importance sampling ratios for each step. The transition probabilities, which are also contained in this probability of the trajectory, are the same above and below the line, so they cancel out. And what we're left with is just the probabilities of selecting each of the actions in the trajectory. I noticed there's a little typo on the slide, just to be clear. The trajectory here was ending in S big T, but here we're actually considering AT as well as a big T. So basically this should have been T minus 1, because this last action wasn't part of the trajectory. That's a minor typo, but the general principle here is hopefully clear. This was discussed before in a previous lecture when we talked about off-policy corrections, and we'll go back to it a little bit more later in the lecture. But, so why do we consider these multi-step updates? We had a simple algorithm, let me go back to this slide first, where we would just bootstrap immediately and make a correction, and we didn't need these awkward importance sampling ratios. So why do we consider them? Well, because this allows us to do multi-step updates, and we've seen before that this can be beneficial to trade off bias and variance. And intuitively, this is depicted in this figure from the book by Sutton and Bartow, where if you consider that a certain path has been taken, if you would just do one-step updating, like in this case with one-step SARSA, you would only ever update the previous state before reaching the goal. And then you'd have to wait all the way until the next episode before we can propagate the information from this newly updated action, maybe backward to whatever action then led to this state. Or maybe a different action leads to the goal, and then you update that one. So credit will propagate correctly if you do one-step updates, but it might be quite slow. And then we argue that sometimes it's better to do a multi-step update. Maybe not full Monte Carlo, maybe not all the way until where we started, but maybe more than one step, just to propagate the information a little bit faster. And one way to interpret this is that this is a bias-variance trade-off, where doing multi-step returns increases the variance, but it decreases the bias of your update, because we're not relying on estimated state values as much. And in addition to that, you can just see that the information will propagate faster in an episode when you do this. Typically, the trade-off is that a multi-step return tends to be more effective, but full Monte Carlo or full TD tend to be worse than doing a couple of steps. So neither full Monte Carlo nor one-step bootstrapping is typically the best trade-off. Now, as I mentioned, this is maybe also quite important for policy gradients, and this turns out to be really the case in practice. So recall that for policy gradient methods, we want to sample something similar to the equation on the slide. For details, I refer you back to the lecture on policy gradients. But we basically get an expectation where the expectation is over the dynamics of the Markov decision process that we're in and over the policy that we're currently following, which is pi. And then we want to estimate this term here, which is the expectation of the actual value of that policy, q pi. This is not an estimate, this is the actual value, times the gradient of the logarithm of the policy at that state and action. And the reason why was explained in the policy gradient lecture. So if you want to remind yourself why this is the equation that we're after, you could look at that. But this would give you, if we could sample this, this would give us an unbiased estimate, a stochastic estimate to the true policy gradient, and would allow us to make our policy better by following that gradient. Now, on policy, we could sample a return, a multi-step return, maybe even a Monte Carlo return, such that the expectation of that return would be equal or approximately equal to q pi. Now, if GT here is a Monte Carlo return and we're on policy, then this would just be an equality even. If full Monte Carlo would be too high variance, and this is the common case, we might actually want to bootstrap, which is why I put an approximate equal here, because GT might be a multi-step return instead of being a full Monte Carlo return. And in that case, the expectation is not quite exactly equal to q pi, but it's typically close, and that's good enough. But what if we're off policy? then this isn't necessarily the case anymore. If we're following mu, then we have to correct g somehow to get a good estimate for q pi. So if the behavior is different, we need to do something to correct, because otherwise the gradient won't be pointing in the right direction. And that's important for policy gradient algorithms, because if we get a wrong estimate for the return here, it might just mean that we're no longer following any gradients, or even we're even following the gradient of maybe the wrong objective. And that means that your policy, for instance, could get worse rather than better. That's not just purely a hypothetical theoretical thing. It turns out to be the case that policy gradients are quite sensitive to off-policy updates. And you have to really be careful that you correct for them. Because if you're too off-policy, a little bit of policy might be okay. But if you're too off-policy with policy gradient updates, the gradient is quite likely to point in a direction that's not going to make your policy better, and sometimes even makes it worse. So that is another motivation for off-policy learning, specific to policy gradients, where it's maybe even more important to correct completely for the off-policyness, or more completely for the off-policyness than in value-based methods. Okay, and now we're going to basically talk about a couple of issues in off-policy learning. So that seems to present so far a solution, but then this isn't the full solution. There are still some problems that need to be addressed, and we're going to talk about that for the remainder basically of this lecture. So these issues can basically be grouped into two main categories. So the first one is high variance, and this is especially true when using multi-step updates, and I'll show this with a numerical example in a moment, why this is especially problematic when we do off-policy corrections, or it can be, and we'll talk about some ways to mitigate this. And then a separate issue is that sometimes you can get divergent and inefficient learning because of a subtle property that if you're going to go off-policy and you're going to correct for that, even if you correct for that in the targets, there's still maybe a mismatch in your state visitation distribution. It's okay if you didn't understand that sentence. I will get back to that later in this lecture and make clear what I mean with that. So to start off, the first issue that we're going to talk about is variance. And this is specific to basically these important sampling corrections in a sense, but it's also somewhat inherent to off-policy learning. And one way to think about this is that we can consider a one-step reward, and then we can look at the expectation of the important samples reward. So for simplicity here, we're first looking at the one-step case, but some of the conclusions here will transfer to the multi-step case, and this is why this is an easier place to start, right? So we're first going to just verify that this is true. So we're going to sample an action under a behavior policy mu, right? And then we're going to correct for that with in this case, we just need to look at one step because we're just looking at the immediate reward. So we're looking at the probability of selecting that one action. And we're going to divide the probability under the target policy that we're interested in, whatever that is, might be greedy, might be something else altogether, by the probability of actually selecting it under behavior mu. And then we just write this out. We say, oh, this expectation can actually be written because we're just sampling the action mu. We can just sum over all actions, or if it's a continuous action space, you could even have an integral here. And we basically look at the probability of each of these actions in the state of interest that we're in, state S in this case. And then we look at the resulting quantity here, which is the random thing over here, is written here explicitly, where RSA is the expected reward when taking action A in state S. And then we see that these mu's, they cancel out by design. So the probability of selecting the action cancels out with the mu that we used in this division, which means we're left with pi, which means we can actually rewrite this as an expectation, but now with the actions selected according to the target policy pi. So this is just to verify that indeed the expectation is the same if you do important sampling corrections, but the variance is not necessarily the same. And we're going to look at that in an example, and sometimes the difference can be quite large. So let's go to the blackboard for a sec, and we'll show an example there. Okay, so you can hopefully see my writing, and I'm going to start by basically specking out what the situation is that we're in. We're going to consider a one-step reward. there's going to be two actions, so let me write them down. We'll have one action to go right, and we'll have one action to go left. And we will also have a reward associated with each of these actions. We don't know these rewards yet, we're going to learn, right? But we do have these rewards for the purposes of our analysis, so we know just for the purpose of the example that the reward of going to the right is actually always just going to be +10, and the reward of going to the left is better, that's +20. And then we have to pick a probability. So let's say the probability of these actions under the target policy that we're interested in is to go right with probability 0.9, so we're more likely to go right, and maybe we go left with probability 0.1. Now, to start us off, right, let's consider the on policy case, where the behavior policy is the same as the target policy. This is what it means to be on policy, that those are the same. And then we can just reason through what the second moment is for the update. So the update that we're going to do will depend somehow, and we're just going to consider the reward itself. So we're not going to actually consider the full update. We're going to have some action AT, and we're going to correct it for the off policiness. Now, because we're on policy, this term will actually just be 1 for now, but in a moment I'll go for the off policy case as well. And this is a term that we're going to consider. We already showed that the expectation of this term for any combination of pi and mu will be the same as the expectation that we wanted under... so let me just write that down. So the expectation of this under mu, we just showed that this is equal to the expectation of RT plus 1 under pi. And this actually holds under any mu and pi. So in the example above in the table, I put the on policy case, right? And I'll do a numeric example in a second. But we already knew this was the case in general. But now actually let me go and not consider then the first moment or expectation, but instead we're going to consider the second moment. The second moment is enough to understand the variance in this case, because the second moment is equal to the variance plus the squared expectation, but because the expectation is the same, we can just look at the second moment instead. Now in this case, because we're on policy, this will just be equal to, let me just write it underneath. As I said, that ratio is just 1 pi divided by mu, so this is just equal to RT plus 1 squared. Right? And because mu is, in this case, in this example, equal to pi, we can immediately just replace mu with pi. And we get the following expectation. The reason I'm doing this is because I'm going to compute the second moment numerically. And then we're going to compare it to when we go off policy. So what will happen here? Well, this expectation is with probability 0.9, we're going to select the action to go right. If we get that action, we're going to get a reward of 10. So the second moment will be 0.9 times 10 squared plus, with probability 0.1, we're going to select the action to go left, and we're going to get a reward of 20. So the second moment will be this in total. With 0.9 we get 10 squared, with 0.1 we get 20 squared. So we just write this out. This will be 90. This will be 40. So we reach a conclusion of our second moment, in this case, turns out to be 130. So the variance, let's make that final step, right? The variance of this quantity, I'm not going to write it out again, is going to be, as I mentioned in words just now, but let me just write it out. Let me actually put a random variable in there to make it a little bit clearer. So let's call it x. This is a generic truth, the expectation minus the expectation squared. So we can see the second moment that we just calculated here, and we can see the mean there. in this case, the expected value, let's quickly do a back of the envelope calculation of that. The expected value of this reward is going to be 0.9 times 10 plus 0.1 times 20, which is just 9 plus 2, so that's 11. So what do we have here? So we know that the variance is 130 minus 11 squared. 11 squared is equal to 121. Please check my math. Which means that the variance is 130 minus 121, which means it's 9. Or if you prefer, the standard deviation is going to be the square root of the variance is going to be 3. Okay, so we did the on-policy case here, right? So we basically are just going through a numerical example. And now what I'm going to do next is I'm going to change it to an off-policy case, and we're going to compare what happens to the variance in that case. Okay? So maybe let me do that by introducing a new color. Maybe I'll use green. And I'm just going to change some things. So we're going to introduce a change to the behavior policy. Instead of having 0.9 and 0.8, let's sample uniformly. So both actions now have a probability of being selected of 0.5. Okay? Now, some things change, because now this is no longer an equality. So let me go back and erase this. We're going to write it out carefully. I'm going to show you that it's something different. So this is all for the old case, right? We're going to recompute that for the new case. So what is this thing? So this is, let's write it out, a summation over actions, probability of selecting that action, times that thing that is in the expectation. And notice that there's a square there, so what we get is pi a squared divided by mu a squared r s a squared. Now notice that something different happens here from the expectation case. The mu that we're multiplying because of the probability that we're actually taking that action cancels only one of the mu's in the ratio. So what we get here is we can rewrite this as, let me pull out one of the target policy probabilities. We cancel out one mu, so we can cancel out this one with one of the mu's in the ratio, but there's one left. So let me pull out one probability. There remains one because we had a squared, and there remains one mu as well. So what we get is this new quantity. Let me make a little bit of room. Let me get rid of the generic fact over here. And then I can continue. And I can say, okay, this is apparently going to be equal to the probability of selecting the action under the target policy times this ratio times the reward squared. So let's pick again, let's just write it out for the explicit calculations. So what we have now is, again, we pick the action under the target policy. We pick the action to go to the right with probability 0.9. But instead of just multiplying this with 10 squared, there's a different thing here, which is 0.9 divided by 0.1. And that is times 10 squared. So this ratio here is new to the on-policy case. That wasn't there before. Similarly, if we pick the other action to go to the left, we will have... Oh, sorry, I made a mistake here. Let me go back. Let me correct that mistake. The behavior policy here wasn't 0.1, it was 0.5. That was just a little fluke. And the ratio here is we pick under the target policy, under pi, those are all target policies, we pick the other action, and then the ratio will be this thing. 20 squared. Okay, so now let's just write that out. What is that? What are those numbers? Well, it's a little bit less obvious perhaps, so feel free to check my math, but maybe let's just write it out. We basically get 0.9 times 1.8, that's that ratio, times 100, plus 0.1 times 0.2 times 400. And this is going to be equal to, let me put that on the next line. Get rid of the previous. If I did my math correctly, this is 162. We can do this one first. It's 90 and then plus 0.8 times 90. So that's 90 plus 72. So that seems correct. Plus, this is 0.02 times 400. So that's 8. So what we get is that in total, this second moment now is going to be 170. Okay, so what is the variance then? The variance in this case is going to be 170, and we're still going to subtract the expectation squared. The expectation did not change, that's still 11. This is still the expectation in the off-policy case, because we've corrected, right? The expectation, by definition, because we're using this importance sampling correction, did not change. So we're going to compute the variance by taking the second moment and then subtracting the mean squared, which will be 170 minus 121 will be 49. So what is now the standard deviation? In the off-policy case, we find that the standard deviation is square root of 49 is 7. Substantially higher. The standard deviation is more than double from what it was in the on-policy case. This is just a numeric example, but in general, one can prove, and feel free to play with this a little bit, try more numerical examples, or maybe even try to prove in general that the variance will increase if you do off-policy corrections. This makes intuitive sense, typically, because under some conditions it will increase. But the intuition behind this is that we're going to zero out some of the returns that happen, and we're going to upweight other returns that happen, especially returns that are rare under the target policy, but they are very common under the behavior policy. They will be downweighted. But the other one is what increases the variance, which is the things that are very common under the target policy, but rare under the behavior policy. So the example here is actually the behavior policy. None of them are particularly rare, but we have this ratio here. Let me highlight that with a different color so it's easy to see where I'm writing. So this ratio here is the ratio that is increasing the variance in some sense. It's where the target policy is fairly high, 0.9, but the behavior policy is lower than that. It's 0.5. Okay. Now let me go back to the slides. Now it actually turns out that in some cases, the variance of important weighted returns can even be infinite. There's an example in the book, I believe it's example 5.5, where you have a very simple Markov decision process. And the target policy and behavior are also quite simple. There's a left action and a right action. And the behavior policy is similar to the example I just gave, is uniform. In this case, the behavior policy is depicted with a B rather than a mu, but it's the same thing. And the target policy always moves left. Then turns out, if you take Monte Carlo estimates, the variance of this can be infinitely large, and this can exhibit itself as shown in the graph, where you can get these spikes, and these spikes will continue to happen. And the reason why is that the variance is literally unbounded in this example, which means that there's always a probability of getting something that is so high that even your average can get polluted by it. Infinite variance is typically a bad thing. Now, of course, there might be ways to limit the variance by making it non-infinite, right? You could, for instance, just have a hard cap on something. You could like put some heuristic in there to make sure that the variance is at least finite. But that doesn't really solve the underlying problem, which is that the variance is just very high. But it's interesting to note that the variance can be actually so high that it can be infinitely large when just doing naive importance sampling corrections. So we might want to mitigate this variance, right? We want to reduce the variance, and we're going to talk about multiple different ways in which we can reduce the variance. So we will discuss specifically 3 different strategies. One is per decision importance weighting, which is an older idea. It's some 20 years old now, but it's quite useful in reinforcement learning. It gets rid of some unnecessary variance, completely unnecessary variance in our updates. We will also talk about control variance. I will explain what I mean with that. And we will also talk about bootstrapping again, and specifically adaptive bootstrapping, which will allow us to kind of pick, in some sense automatically, by looking at the importance sampling ratios when to bootstrap, when it's important to bootstrap to minimize the variance. And we'll start with, as I mentioned, per decision importance sampling. Okay, so what does this term mean, per decision importance weighting? We're going to consider some state S, some arbitrary state, and we're going to look at some random variable x. So think of x here as, for instance, a reward. Now, we're going to basically observe that for any x that does not correlate with the action, we don't actually need to importance sample. So this is written here on the slide. Look at the left-hand side first. We have the expectation of this random variable x, for instance, your reward, under the target policy pi. This is the thing that we want, right? We want this expectation. We noted before that this is actually equal to the expectation of x under the policy mu, as long as we multiply it with this importance sampling ratio, right? But now what we're claiming is that if x is uncorrelated with the action, that this thing is actually equal to the expectation of the uncorrected random variable x. Intuitively, this makes sense. If x does not depend on the policy, we don't actually need to correct, because the expectation will be about everything else that is random. It will be about your MDP, for instance, right? But if it doesn't depend on the action, then the policy shouldn't matter. We shouldn't need to correct. Now, why is this a good thing? Well, this means that we might be able to have lower variance than otherwise by basically not adding this additional variance that we do with these corrections and just ignoring the random variables that don't correlate with the actions under consideration. So let's first prove this fact, and we're basically just going to do a very simple derivation, so you can also kind of check the assumptions that are being made here, right? We start off with this importance sample corrected random variable x under the behavior policy mu. Now, because this ratio is a random variable, but it's only a random variable because a is a random variable, right? So if a does not correlate with x, this means that we can write this expectation as a multiplication of different expectations. You can only do this when these random variables x and this ratio do not correlate with each other. But that's the assumption that we're making, that they're uncorrelated. Now, if that is the case, we can just unpack this last thing, and this is an important property to be aware of in general. The expectation of the importance sampling ratio itself under the behavior policy is always equal to 1. We're going to prove that here by just writing it out. So again, we're going to sum over all of the actions, look at the probability of selecting the action, multiplying that with the ratio. As usual, the behavior policies cancel out. Apologies for the sk here, that's just small s. This is a typo on the slide. So these cancel out with each other. What is left is just a summation over actions for the target policy, but because the target policy is a proper policy, this will equal to 1, so we can just cancel it out, it disappears. So this shows that the expectation of the corrected x is equal to the expectation of the uncorrected x, if x does not correlate with the action. This is a general statement, as I said before, so the expectation of the ratio itself should always be equal to 1. Only of the ratio itself, right? It's not if we multiply with something, then this ratio does not disappear, as we saw before. You can actually change your expectation by adding this ratio, but the ratio by itself is always equal to 1. This can also be useful if you use these things, for instance in experiments. This could be a useful check that on average your importance sampling ratio itself should always be on average 1. Now we're going to apply this to reinforcement learning, but in order to do that we're going to introduce a little bit of common notation from the field to be able to condense the notation quite a bit and hopefully make things quite clear. So the most important thing here to keep in mind is that rho is the new notation that we're going to use for this importance sampling ratio, because this term shows up all the time, right? And it's quite a large term to keep on writing down. So the importance sampling ratio for the different policies at some time step t, we will condense that notation into rho t. So the t here refers to the states and to the actions, and implicitly rho depends on the target policy and the behavior policy. Now, in addition to that, we can introduce this other notation where we can consider rho from time step t to time step t plus n. And this will simply be the multiplication of all of the rows for all of those time steps, which, by definition of rho, is just a multiplication of the importance sampling ratios. So we will call rho the importance sampling ratio. Rho could be thought of as ratio, right? So this might be a useful point to remember. And if we do that, then we can condense the notation quite a bit. So the thing that we're interested in is the return, which I've written down here explicitly for an episode terminating with a final reward at time step big T. So the return is just a summation of the discounted rewards as usual, starting at time step T, because we're considering the return at time step T. In order to correct this return, if this return was generated according to some behavior policy mu, but we're actually interested in target policy pi, then we can multiply with this importance sampling ratio for the full duration of the trajectory. So in this case, the return spans a trajectory from time step little t to time step big T, and that means that we're going to correct with all of the actions in that trajectory multiplied together, all of the ratios multiplied together, which with the new notation we can just write down as the ratios from t to t minus 1, big T minus 1. So this gives us a very condensed, nice notation where this is the total ratio, which captures the probability of the trajectory under the target policy divided by the probability of the trajectory under the behavior policy. And we multiply the return in order to make it an unbiased estimate for the return under the target policy. However, we can also note that this return is actually a summation, right? A summation of individual rewards. So instead of perceiving this ratio as correcting the full return, we can also push it into this summation and apply to each of the individual rewards within that return, right? The return is just a sum, so we can push this ratio through the summation and multiply it with each of these individual rewards. But this raises a really interesting question. So is this the right or the best importance sampling ratio to be applied to each of these individual rewards? And turns out maybe we can do a little bit better. So what we're going to do here is we're going to get rid of some terms that we don't need. So we're just going to remind you, rho t to big T minus 1 is the importance sampling ratio for the full trajectory that spans, that this return spans. And we could push it inside the summation that this return actually is by multiplying each of the individual rewards. But now we're going to recall this fact that I mentioned before, and we're going to note that earlier rewards cannot depend on later actions. When you've received a reward, you can't change that reward in hindsight by picking actions later on, right? This just violates basic causality. So this means that the rewards that happened earlier, if the policies are fixed, which we're considering here, we have a fixed target policy and a fixed behavior policy, then earlier rewards cannot correlate with later actions. Later actions have no influence on these earlier rewards. This means that for each of these individual importance sampling ratios multiplying each of these rewards, we can actually truncate them up until the action that was just before the reward. We're basically cutting off all of the actions that happened after we've already received this specific reward. What does this mean? Well, this means that this is an equality if they don't correlate, right? The actions after time step k cannot influence the reward we've received at k plus 1. This means that these expectations will be equal even if we ignore those ratios because of this earlier property that we talked about, where the ratio, if it's uncorrelated with the random variable that you're multiplying, then you could just pull them apart and the ratio will be equal, the expected ratio will be equal to 1, so it disappears from the expectation. But this doesn't mean that these have the same properties. In fact, this term here might have much lower variance in some cases, because it's basically a shorter partial trajectory that we're considering, right? Now, interestingly, and maybe kind of like aesthetically pleasing as well, is that this new thing can be written down recursively quite nicely, as shown here. So we're considering, in this whole slide, we're considering Monte Carlo returns, right? We're not considering bootstrapping. We'll get back to bootstrapping later. But for clarity, we're just considering Monte Carlo returns for now. And then this term here can be written down as follows, where at time step t, the importance sampled return, denoted here with this superscript rho, will apply an importance sampling ratio, but just one. Just the importance sampling ratio is corresponding to that time step, to the reward, and to the next return at the next time step. Recall rho here, rho t, is simply the division of the target policy at that time step only with the behavior policy at that time step. So what we're basically saying is, oh yeah, we get a reward, we need to correct for the fact that we took this one action under the behavior policy, but it might have been a different distribution, the behavior policy, than the target policy. So we need to correct for that. And we also need to correct the rest of the return. But the subsequent corrections on all of the future time steps, t plus 1, t plus 2, and so on, they're recursively within this term, right? At the next time step only, we're going to apply rho t plus 1, and then rho t plus 2 at the time step after, and so on. So instead of multiplying, for instance, this first reward with the importance sampling ratio that would correspond to the full trajectory, we're only multiplying it with this one step. And this can reduce variance quite a bit, and especially if we later combine this with bootstrapping. And this is called per decision importance weighting, because we're only adding each importance sampling ratio essentially when we need it and no earlier. And this means that if you then write this out, it will be equivalent to this term, where each of the rewards get multiplied at least with the first importance sampling ratio, but only the later rewards also get multiplied with later importance sampling ratios, rather than indiscriminately multiplying all of the rewards with all of the importance sampling ratios. So we have this recursive definition, and now we know and we can prove that the expectation of this return will be an unbiased estimate for v pi. Even if, so rho corrects for the mismatch between the target policy pi and the behavior policy mu. So the assumption here is that we're generating the data under this behavior policy mu, but then g rho will be an unbiased estimate for v pi. So we can use this in a TD-like update, for instance, right? Or a Monte Carlo-like update. We could also do the same for action values. There's a slight subtlety there, because for action values, we don't need to correct for the first action because we will already be conditioning on having taken that action. If we want to learn action values, we typically say, okay, we have some states, say st, we took some action at, and we want to update the value of that, conditioned on the fact that we were in that state and already took that first action. What does this mean? We need a slightly different return, one that doesn't apply the first importance sampling ratio because the first action is already given, right, when we update our action values. This means that we should only apply the importance sampling ratios a little bit later. So again, this return will apply the importance sampling ratios on a step-by-step basis, on a per decision basis, but it will start basically one step later before it applies the first one. Then on the next time step, rho t plus 2 gets applied, and so on and so on. So I just want you to basically take a moment to reflect on this, how and why these are different and what that actually means, and convince yourself that these are both appropriate terms. So this one is unbiased for v pi is the claim, and this one will be unbiased for q pi for the state action that we already took. So for st, at. Okay. Now we're going to move on to the second topic to reduce variance, which will be control variance. And to explain control variance, I will actually start by showing an example. So we're going to go back to the blackboard, if you will. There we go. And we're going to do a very similar example to before. So let me just start first by, let me use white. I'm going to start by writing now the action. And let's just consider the immediate reward case first. We're going to go discuss the sequential case in a moment. But let's first do the immediate reward case, where again we're going to define an action, a reward, a probability of the action, and a probability under the behavior policy of the action. So again, let's maybe consider an action that goes to the right or to the left. Let's make the rewards very simple. Let's say to the right is +1 and to the left is -1. Let's also consider a very simple target policy. We're only interested in estimating what happens if you go to the right. Right? Of course, by inspection, you could very easily determine already what the value is, but that's not the point. We're going to basically try to estimate this from data. We don't actually know the rewards, and maybe they might actually also be random. You don't know that in advance. So what we're going to do is we're just going to consider an update to our value function, and let's consider the tabular case just for simplicity, right? So our update to the value function, let's call it dvst. So the value of st, or actually let's not even put the state there. So let's just call this vt. So the value is going to be an estimate of the expected reward under the target policy. So our update to the value is going to be defined as some step size, as usual, times the reward that we get. And we're going to multiply that reward with rho, right? We're going to correct the reward so that we get the right expectation. And we're going to take our current value and update it towards it. This is the tabular update, so there's no times gradient or something, just for simplicity. So what is this? We can just write it out, right? There's two cases. Either we picked the action to go left or we picked the action to go right. And the behavior will actually pick each of them with equal probability. So what happens here? Let's just write out the cases. If we pick the action to go right, our update will be alpha times the importance sampling ratio when we go right. What is the importance sampling ratio when we go right? It's going to be pi divided by mu. So what we get is the pi right divided by mu right is going to be 1 divided by half is going to be 2. Okay? So if we picked the action to go right, we get rho equal to 2 times the reward that we get, which is 1, and we're going to subtract our current value. So what is our current value? It doesn't really matter for the purpose of this example, so I'm just going to put vt. This is if the action was gonna go right. And of course then the alternative is if the action is to go left. The importance sampling ratio then has 0 divided by half, so this will just be 0 times -1, but the -1 doesn't really matter, of course, because we're multiplying by 0 if the action is to go left. Right? So we basically get that we either, let's actually write that again. So the updates are either basically update your value towards 2 or update your value towards 0. Now you may have already done the math. It's not too hard. Our actual reward on going right is always 1. And indeed, this is doing the right thing on average, right? Because we 50-50, we pick the action to go right or left because the behavior policy is 50-50. And in one case, we update towards 2, and in the other case, we update towards 0. So on average, we're updating towards 1. We're doing the right thing. We're updating towards the right return. But why would we do it like this? Why would we update towards this arbitrary value of 0 when we take an action that the target policy would never take? Well, it's because to get the right expectation, but is there something else that we could be doing? Is there something maybe a little bit better that we could be doing? So let's change the update now. Let's consider a separate, different update. And what we're essentially going to do is the following. We're going to pull out, and I'll explain in a moment why we can do that, the row outside of the brackets. So this first part is the same, right? We are multiplying the row, the importance sampling ratio, with the reward, but it now also multiplies the value. The reason we can do that is because the row and the value, they don't correlate with each other. And that means that in expectation, row times v is the same as v. Now, let's go through the example. What does this mean for this specific example? Let's just go through the cases again. We're going to have alpha times 2, because the row is now outside of the brackets, plus 1 minus vt, if the action is to go right. But if the action is to go left, we're going to multiply the whole error term here with 0. Because this is our importance sampling ratio, row. So what does this mean? Well, this means that if we're going to go to the right, we actually can consider this to be an update with a step size of 2 alpha towards 1. Oh, nice, we're updating towards 1, which is exactly the right value to update towards, right? If the action is to go right. And when the action is to go left, we just don't update at all. So you might notice here that this is lower variance because we either update towards 1, which is the value that we actually want, or we don't update at all. So when the value becomes equal to 1, so when our value estimate becomes accurate, this second update just stops updating. Whereas the first update that we were doing would continue to update with updates that are on average they're correct, but they continue to bump around, right? You continue to update towards 2 and then to 0, maybe to 0 again and then to 2 again, and in the end it all works out. But this second update is lower variance because it will just update towards 1, and when you've already reached 1, you're done and it doesn't actually update anymore. The error will simply be 0. So that seems intuitively to be a good thing, right? And indeed, we can show that the variance of this update is going to be alpha squared, step size squared, if I did my math correctly. And the variance of this update will be 0. Both of these are under the assumption that our estimate is accurate. So this is what I just mentioned essentially. Let's consider that your v is already 1. So let's say that explicitly. If vt is already good, if it's already 1, then the variance here will be alpha squared, because we either update with alpha up or with alpha down. Do you see that? 2 minus 1 is 1, so we either update up with alpha, and 0 minus 1 is minus 1, so, or we update down with alpha. So we're continuing to update with whatever the step size is. Where in this second case, if value is already accurate, vt is already 1, then our variance is simply 0 because the error will be 0. So that looks good, right? We've lowered the variance. Now obviously this is somewhat of an extreme example because the estimate is already correct, but it turns out this principle applies more generally. And what we've essentially done here is we've added a control variance, that's how it's called, and we've kind of done it implicitly, but I'll now talk about this a little bit more explicitly so we can better understand exactly what's going on. But let us first return to the slides. Okay, so continuing. We can extend this idea of using control variance to the multi-step case. Let's first do that. And in order to do that, we're going to consider a generic multi-step update here. We're going to consider the lambda update. So instead of just assuming Monte Carlo for simplicity, we're actually going to allow bootstrapping now. And recall that this lambda return, basically on every step, so the lambda return is defined to just take the first reward and then discount. And then on the next step, it bootstraps with some weight, 1 minus lambda, or it continues. Oh, sorry, there's an additional gamma here. There's already a gamma outside the bracket, so the second gamma should disappear. So it's either weights the bootstrap target with 1 minus lambda or the rest of the return with lambda. Here the gamma lambda is correct because now we've pulled out these terms out of the expectation. And we can rewrite this, we've also mentioned this before in a different lecture, that you can rewrite this as the one-step temporal difference error plus the discounted and additionally downweighted with this lambda parameter recursive lambda-weighted temporal difference error. So the lambda temporal difference error, which is just your lambda return minus your current state estimate, can be written recursively as the immediate temporal difference error plus the discounted with additionally lambda recursive itself. So check, just as a sanity check, that if lambda is 0, we get 0, we get one step TD back, TD 0. If lambda is 1, this will turn out to be equivalent to the Monte Carlo error. So this is just reiterating what the multi-step case looks like. And then this idea of control variance can be applied there by basically weighting the errors rather than the return. So basically we have this minus v part inside here. We're going to do exactly the same trick as we did in the example. And this is going to often reduce variance. It doesn't actually necessarily reduce variance, but it often reduces the variance. And this is sometimes also called error weighting. Now, why does it reduce the variance? So let me, in order to basically talk about that, let me actually go back to the whiteboard. And the idea is now that we basically had, let me do the one-step case first. So we had this first thing, which was rho t times rt minus vt. So why do I keep using this term control variance? Because we're going to replace this with this second term, right? So this is 1, and then 2 is a different term where we pulled the rho t outside. And we're going to note that this is, of course, equal to rho t rt. Let me just push it inside. That's 1 minus rho t vt, right? And that's going to be equal to rho t rt plus 1 minus vt plus 1 minus rho t vt. So we get, if we call this 1, that 2 is equal to 1 plus this additional term. So what is this additional term? Well, the expectation of this additional term, 1 minus rho t vt, I'm going to claim, actually let me be a little bit more explicit and put the behavior policy there. I'm going to claim the expectation of this is 0. Well, why is this 0? Because this thing is going to be equal to the expectation of 1 minus rho t times the expectation of vt. If we would be conditioning on state here, this final expectation wouldn't even be an expectation, would just be the value of that state. I'll just keep it in the expectation just for clearness. But note that the value at that time step doesn't correlate with the importance sampling ratio because we're considering the importance sampling ratio of the action after taking the state. So we can pull that out if we could correctly condition on everything. And this term over here is going to be equal to 0 because the expectation of rho under the behavior policy equal to 1. So we get 1 minus 1 is 0. So this full thing is equal to 0. So what does this term do then? This is our control variance. So implicitly by weighting the error, which we were doing over here, rather than just the target, which we were doing over here, then what we're doing is implicitly we're adding this control variance, which we've written over here. What this is doing is there's a different term which has expectation 0, but it varies along with the thing that we're interested in. So the thing we're interested in is this thing over there, number 1, if you will. But we've added a separate term at the end, which has expectation 0, but because it varies along with the thing that we're interested in, you can reduce variance. And that's what it's doing. That's in general called a covariate. So we can view this error weighting that we were doing as essentially applying covariates, adding terms that reduce your variance but do not change your expectation. There's more discussion about this in the book, so feel free to consult that if you still feel maybe slightly confused about these things. I will now return back to the slides where we've applied this idea to the multi-step case by basically weighting the errors rather than weighting the returns. And we've written that down recursively here, where we have this new notation delta rho lambda, where the rho indicates that we're importance sampling, and the lambda just indicates that we're partially bootstrapping along the way. And the rho's now apply to the errors rather than to the returns. So this, by design, includes those 1 minus rho v control variate terms that we've just seen on the blackboard, if you will. And as I mentioned, this is sometimes called error weighting, in contrast to reward weighting, or per decision importance sampling. But we can apply this like in the per decision case, of course, as well, which you're already doing here with this equation at the top, right? We're not applying the full ratio for the full trajectory. We're just doing this on a per step basis. And one can then show that the expectation of this under the behavior policy is equal to the expectation of if we would only apply these things to the return and then just subtract v as normal. The expectations are equal, but the variance is not necessarily equal. And oftentimes the variance on the error-weighted term is lower than that on the return-weighted term. This is, by the way, not necessarily the case. We once wrote a paper where I was involved in as well with Rich Sutton and Rupam, I believe, Rupam Mahmood and Dqn Algorithm. And there we at some point thought maybe we can prove that this actually has lower variance in general. Turns out it doesn't. There are counterexamples. But in general, it seems like, more generally speaking, it often has lower variance. You just can't say it always has lower variance. It doesn't necessarily have lower variance. But as the example showed that I showed you before, it makes intuitive sense to weight the errors, because essentially it means that you don't update when you get data that is irrelevant, rather than arbitrarily updating towards 0 and then updating towards higher numbers later to correct for that. Okay. So typically this is why I say that this error-weighted term can have lower variance. In practice it often has lower variance. You just can't say that generally it always has lower variance. Okay, that brings us to the end of that topic of control variates, and now we're going to go to the next topic to reduce variance, which will be adaptive bootstrapping. So we already talked about bootstrapping quite a lot, obviously, and bootstrapping is typically a good way to reduce your variance a little bit, and we already had these lambda weighted errors or returns where lambda could be lower than 1, right? And if a lambda is lower than 1, then we're going to reduce the variance, but we might incur some bias because we might bootstrap. The bias is not because we are estimating for the wrong distribution necessarily. The bias is there because we're using estimates. Our value function won't be completely accurate, and therefore there might be some bias due to our function approximation error or just our estimation error because we have seen finite data so far. So for action values, we can use this importance sampled return, where you can see the normal thing showing up here. This is the expected SARSA return. So we're doing the one-step case here if lambda is equal to 0, but lambda can be different than 0, and if lambda is different than 0, then we basically recurse and go into the next time step, right? So this quantity here is defined here recursively, and we can see if lambda is 0, we can see the expected SARSA thing reappearing that we had previously, which is shown here on the slide as well. And there's no importance sampling then. We already discussed this slightly earlier in this lecture, right? Where we could just bootstrap and wait with our target policy, and then we're doing corrective policy updates in some sense. But we are relying on these estimates, and these estimates might not be accurate, and therefore we might not want to do that. And we can see here in the equation, if lambda is 1, then this bootstrapping term just completely disappears, and we find the important sampled return for action values that we saw on an earlier slide again. So this smoothly interpolates as per usual with lambda between 0 and 1. But there's a problem if we bootstrap too much, which is specific to the off policy case. So I already said, oh yeah, maybe your estimate's somewhat not great, so you might bootstrap and that might not be too great. There's a completely different reason why this bootstrapping might be harmful. It might open you up to what is called the Deadly Triad. So let's recap what that is. The Deadly Triad refers to the possibility of divergent learning when we combine bootstrapping with function approximation and off-policy learning. It only shows up when all three of these are present. Unfortunately, they often are. If you want to do what is nowadays called deep RL, we're clearly doing function approximation because we have deep neural networks to approximate our value functions. We're often doing bootstrapping because just doing full Monte Carlo rollouts would be very much too high variance in many cases, and therefore learning would be quite slow or ineffective. And we're also often doing off-policy learning. For instance, the Dqn algorithm, the well-known Dqn algorithm, which was used to play Atari games quite successfully and has sparked a lot of follow-up work as well. It uses Q-learning, which means that we are, in the original Dqn, we're actually bootstrapping after just one step. It's one-step Q-learning. In later iterations, such as Rainbow Dqn, to name one example, this has been extended to multi-step updates, but still, after, say, 3 or 5 steps or something like that, typically we bootstrap. Because it just turns out to be more effective that way. The variance will be lower and the updates will be better. But it does mean that we're combining all these three things then. We're bootstrapping, we're doing deep neural networks, so we're doing function approximation, and we're doing off-policy learning because we're using something that's Q-learning-like. We're bootstrapping with a max at the state where we bootstrap. So to recap, so why does this happen? So we saw this example before. So we have two states here. The rewards are always 0, but we're only going to consider this one transition, and we only have one feature. The feature value here is 1 in this first state, and the same feature has a value of 2 in the second state. We only have one parameter, w, and our value function will be linear, so it will be w times x, which in this case, first state is just w, and w times x in the second state will be 2w, because the feature value has value 2. The optimal value function is within reach. If we would set our weight parameter w to 0, our estimates would be perfect. But if we use TD learning, one-step TD learning on this transition, then something happens that we don't want. So our value function, the weights of our value function will be updated according to one-step TD learning as shown on the slide. And if we fill in all the values, so we put R0 here, the value of the next state will be 2w, and the value of the current state will just be w. The gradient will just be 1 because, will just be w because the gradient of our, no, sorry, I'm saying this wrong. The gradient will just be the value of the feature, which is for this state 1, right? So the gradient here is, because it's linear, is just x, and x in the state that we're interested here is just 1. So we're multiplying this whole term with 1. I got distracted slightly with the w here, but the thing that happened here on this step is that both of these values have a w in there, and we just pulled it outside of the parentheses. So this total update, you can verify this by carefully, slowly stepping through it, will look like this. And then we can note that if the discount factor is more than a half, which is of course quite a common case, then in this specific example, if the weights are already positive, then this term will also be positive, which means that the next weights will be even more positive. Similarly, if the weights are negative, then the next term, this term will be, within the brackets will be positive, but the weights are negative, so the total term will be negative, which means that the next weights will be more negative. So in both cases, we're updating away from 0. And in fact, we'll update away faster from 0 the larger your weight becomes, the larger the magnitude of the weight becomes. This means you'll exponentially quickly diverge to either plus infinity or minus infinity, depending on where your weight started. So that's problematic, and that's an example of the Deadly Triad. And it happens because we're updating off policy, which in this case refers to the fact that we're never considering any updates from this second state. So although we go there, we never update by going away from it again. That is why this example is off policy. So we can use multi-step returns as well. So let's expand the example, and then let's now consider also the transition that moves away from this second state. And instead of just using one-step TD, let us consider a lambda return. We're still only considering updating this leftmost state. So we're still going to update off policy, where with off policy here I mean that the state visitation distribution does not correspond to our behavior. Our behavior steps through these states as follows. We start here, then we go here, and then we go there, right? And then we terminate. So we spend equal amounts of time in the first state as in the second state under our behavior. But the updates will conduct off policy by basically only considering updates from this first state. Now, if we consider the update to the leftmost state, we see if we just expand everything, that this additional term of 1 minus lambda appears. Compared to the previous slide, where we saw that the update would be w plus alpha times 2 gamma minus 1 times w. If you just write out this update, where the rewards are both 0, you get this different equation where, depending on lambda, this 2 times gamma term gets downweighted. This actually means that this multiplier to the weights will be negative whenever this equation holds, whenever this term is smaller than 1. This means that if lambda is larger than 1 minus 1 over 2 gamma, then whenever your weights are positive, they would go down rather than up. And whenever they're negative, they will go up rather than down. So if this condition holds, if your lambda is large enough, it becomes a convergent algorithm where the weights will now be updated towards towards 0 rather than away from 0. This is specific to this example, right? I'm giving you specific equations, specific conditions to lambda, which basically take into account the full example. And this 2 here, for instance, comes from the fact that the feature vector, the feature value here is 2. But the general gist of it is true, which means that if your lambda is large enough, you're good to go. You won't have any problem with the Deadly Triad. And this makes sense because the Deadly Triad was about bootstrapping, function approximation, and off-policy learning. The larger you set lambda, the less you're bootstrapping. The extreme case is when you consider lambda equal to 1, in which case we're using Monte Carlo returns, we're not bootstrapping at all. If that is the case, you can update off policy, you can use function approximation, you won't diverge. But if you want to still bootstrap, you can use a lower lambda, it just needs to be large enough. So it's not actually a binary thing. It's not about all bootstrapping is bad, and if you do any bootstrapping, you'll be in the Deadly Triad. No, this example shows that if you just bootstrap less, sometimes you can be fine. Okay, so let's, for instance, consider the example, like if your discount is as low as a half, then this is just saying, oh, my lambda needs to be larger than 0. And that's often the case. If your discount factor is, say, 3/4 or something like that, then this term would be, this whole term would be 2/3. So that means that your lambda needs to be larger than 1/3, if I did my mental math correctly. So basically, the larger your discount is, the larger your lambda needs to be for this to still be convergent. But we can see that there are lambdas that will make it convergent in this specific example. So concretely, if your gamma is, your discount is 0.9, then turns out it's sufficient to have a lambda that is larger than 0.45. That's not a hugely large lambda. We often use lambdas that are, say, 0.8 or 0.9 or something like that. So it turns out if you do that in this example, you're good to go. You can update off policy and you would still be fine. So the conclusion of all of this is just an example, but the conclusion is if we do not bootstrap too much, learning can be a lot better. We might mitigate, if not fully remove, the Deadly Triad. So maybe we can reduce variance by adaptively bootstrapping, because we don't want to bootstrap too much, because then we might get into the Deadly Triad. But we also don't want to bootstrap too little, because then the variance will be very high, especially if we're doing these important sampling updates, right? Because important sampling ratios tend to add variance to our updates. So can we maybe adaptively bootstrap just enough so that the variance is at least bounded, or is at least smaller than it would otherwise be? I'm just going to present you one way to do that. There might be multiple ways you could do that. And the idea would be here to bootstrap adaptively only in as much as we go off policy. So if you don't go off policy, you don't need to bootstrap. You can just continue using the data. But when you go off policy, this makes intuitive sense in some sense, right? You're following a certain policy, you reach a certain state. At that point, in that state, you choose a completely different action that the target policy would never take. Maybe this is a good point to bootstrap. Rather than trying to use this very tenuous data that had nothing to do with the thing you're trying to estimate to somehow still update it. That is possible, but tends to lead to very high variance updates. So there are some intuitive ideas behind this idea, but we can formalize it, which we'll do next. So we're going to start with this important sample corrected multi-step error, right? Recall delta t is just your one-step TD error. We're correcting it to be a good off-policy error, and we're defining it recursively with lambda to make it a multi-step error. Now, we might extend this example slightly by allowing an initial bootstrap parameter. So basically, we're downweighting this whole thing with an initial lambda t. If lambda t, note that lambda is now time dependent. I'm allowing lambda to differ from one step to the other. So that's important because now we can have a special case. We've basically just generalized the thing we had before if we set lambda t to be equal to 1. Right? Then we just get the thing back that we had before. Lambda t plus 1 doesn't also have to be equal to 1 because I've now subscripted by t. So this is a slight generalization from before, and this will just make some things a little bit easier later on. And we can pick a different lambda on every time step. That's what I mean with adaptive. It's two things. It allows us to pick different lambdas on every time step, and we're going to pick the lambda in a data-dependent way. Now the idea is, if we define this thing recursively, look at the recursive definition first. We see that there's a lambda t, rho t. Then there's a delta, and then we go into the recursion. But that means in the recursion, there will be a lambda t plus 1 times rho t plus 1. They always go together. They're always next to each other. And then the idea is, well, this rho, what is the problem with rho? So rho is the important sampling ratio. And we know that in expectation by itself, rho will be equal to 1. Recall that that's just a property of this ratio. The ratio by itself will have an expectation of 1. But we also know that it can increase variance quite a bit. So what happens? Why is it increasing variance? Well, sometimes it'll be lower than 1. Sometimes it will be larger than 1. And indeed, it can sometimes be very large. When is it very large? It's very large when we're dividing a large target policy probability with a very small behavior probability. That means we've selected an action that was very rare under our behavior, but it's actually a really common action under your target policy. Occasionally that will happen, and this ratio can become very large when it does happen. So intuitively the idea will be, well, what if we pick lambda in such a way that if we multiply lambda with rho, it's always smaller or equal to 1. Then we know that this is bounded. There are no large ratios anymore. So what does this mean? We just rewrite this inequality, and basically it means that we pick lambda in such a way that it's the minimum of 1 or 1 over the important sampling ratio rho. Why this minimum? Well, we don't want lambda to go larger than 1. So basically what is happening here, if rho is itself smaller than 1, which is often the case, right? Smaller than 1 rho basically just means that your target policy wasn't very likely to pick the action, but the behavior policy was. That happens, correct? Right? You might pick an action and the target policy is just not interested in that action. Then this rho can be very small, which means that 1 over rho can be large. If that is the case, we allow ourselves to continue. We allow lambda to be 1. We continue to the next time step. However, if rho is very large, if we picked an action that was quite rare under the behavior, but it's really common under the target policy, then rho can be very large. And then we're saying, oh, but then we're going to pick lambda to be smaller. So whenever we pick an action that was very rare under the behavior, but it's very common under the target policy, let's just bootstrap there. And that's the whole idea, essentially. So when we're too off policy, if rho is very far from 1, we're going to truncate this multi-step error, the multi-step return, if you will. And that's the same as just bootstrapping there. Because the closer lambda is to 1, the closer lambda is to 0, the more we're bootstrapping, right? If it's all the way equal to 0, then we're just bootstrapping fully there. If it's a little bit above 0, we're still partially bootstrapping there. The closer we are to 1, the less we're bootstrapping. So instead of thinking about bootstrapping as a binary thing where we either bootstrap or not, we're thinking about it smoothly. This idea is known as ABTD, Adaptive Bootstrap TD, by Rupam Mahmood, or also as vtrace from a paper called Impala by Lasse Espehold and others. And it's quite an effective algorithm, and we're actually free to choose this, right? We're free to choose different ways to bootstrap. And in fact, in the tabular case, all of these methods will be updating towards some mixture of the multi-step returns, and therefore they're all fine. They all will converge. In deep reinforcement learning, this is an extremely common thing. There's a lot of agents that are using vtrace, and vtrace essentially uses this idea. There's a couple of more things to be said, and I refer to that paper if you want to know more in depth. But it basically boils down to this idea of bootstrapping when you go off policy. And this is an extremely common trick, especially for policy gradients. Because policy gradients, as I mentioned before, really do not like biased return estimates, because if you have a biased return estimate, then you're no longer necessarily following a policy gradient. And of course, that might be harmful, right? It means your policy is no longer necessarily improving. In fact, it might be getting worse. So vtrace is very common, and this is a very important trick, and it really helps reduce variance. Because we're basically just truncating away parts of the returns that would give you very high variance. But as long as the variance is okay, we're just allowing yourself to continue and to use multi-step returns. Okay, now one final thing which is very related, but it's a different way of doing this, is the algorithm called tree backup. So I mentioned there's different ways you could bootstrap, and picking the trace parameter adaptively, as we were just doing before, is not the only way. A different thing we could do is to first start with the Bellman equation, and then we're going to go to the multi-step case. And effectively what we're going to do is just first muse on this equation for a bit. This is the definition of the action value for the policy that we're interested in, pi. And we know that from the Bellman equation that this is the expectation of the reward, given that you have seen this state in action. And then in the next state, following that policy in the next state, and then picking the action according to that. This is also where this expected Sarsa update comes from, right? It just samples this. Note that the expectation does not depend on the policy, because we're already conditioning on the action A. This is saying, given that we have a state and an action, what will be the value of the policy? Well, we only need to consider the policy at the next step. We don't need to consider it on the first step, because we're already conditioned on the action. So to sample this, we can sample it as before. We could bootstrap immediately, but a different thing we could do is basically we can pull out the action that we're going to select on the next time step, because that's the action that we've actually sampled, and we can just replace the estimated value that we had for all of the actions with the return given that action. So what are we doing here? We're replacing this summation over all of the actions by simply pulling out the action that we're actually going to take on the next time step. We're going to turn this into a multi-step update, and we are keeping the weighting, right? Because this is a weighted sum of action values, and what we're basically going to do is we're going to use these as expectations. These are estimates of the expected return, right? And we're going to replace only the one return that we actually had. So the way to think of this is think of a tree. At the root node, you're in a state. There's a whole bunch of actions. And the value of the root node for a specific policy would be the policy weighted sum of the values of these actions, right? But what we're going to do is we're going to actually select one of these actions, and for that action we can replace the estimate with the value, the return that we sampled. That's exactly what's going on here, except we're deferring it one step because we're not conditioning just on a state but also on an action. So the first state and action are already given, but then at the next step, so basically the next node in the tree, we're going to consider all of the actions, and all of the actions that we haven't selected, we're going to use the estimates that we have, appropriately weighted according to the policy. But for the action that we did select, we can actually use the sampled return. It's defined recursively, so the next step you might bootstrap again on all of the actions that you didn't select, and again continue just with the action that you did. So we only remove the expectation of q st plus 1 at plus 1, which is the action we actually selected, and we replace that with the sampled return. This is unbiased and it's very low variance because we don't have any importance sampling ratios. There's never a division by mu, right? The pi here in fact plays a role that's quite similar to lambda. Of course, we can add an additional lambda and downweight it even further. But there's a problem, which is maybe it's a practical problem. Sometimes this works amazingly well, but there is a bit of a practical problem that sometimes you might bootstrap a little bit too early, and therefore you need to be careful of deadly triads. If pi is not your behavior, like if your behavior is something different, which is perfectly fine for this method, this is an off-policy method, but if your behavior is different, you might be bootstrapping very much after a first step. Let's consider that there's many actions here, each of which have a quite low probability. Then this is very similar to just bootstrapping after one step. However, if your policy is fairly greedy, then it might be that you actually take a number of steps before you bootstrap. In fact, I didn't put this on the slide, but if your policy is the greedy policy, then what this mechanism would be doing is essentially it would take as many steps as your policy agrees with the greedy policy. So as long as you're picking greedy actions, and if the greedy policy is the target policy, like if you're interested in a greedy policy, then this method would, as long as you're picking greedy actions, would continue to roll out a trajectory. But at the moment that you select a non-greedy action, it would terminate there and then bootstrap with a max Q. So a Q-learning-like bootstrap target. That is actually an algorithm that was already proposed by Chris Watkins when he proposed the Q-learning algorithm. And if your policy is fairly greedy, then it can actually have long multi-step returns. But obviously, if your policy is quite uniform, but you're interested in a greedy policy, then the returns might be truncated quite a bit. This is more generically true. This equation is not just for a greedy policy, a greedy target policy. The target policy could be greedy, but doesn't have to be. But it has the same issue that if your behavior mismatches a lot with this target policy, then you might bootstrap all the time. And that might be a little bit dangerous because of the Deadly Triad. There are, in fact, other ways to deal with the Deadly Triad. There are solutions for this, but no... basically, we don't know yet what the best solution is. There's multiple solutions to the Deadly Triad, multiple algorithmic innovations or different ways to think about this, some of which are included in the book by Sutton and Bartow. But we don't know for sure yet what the best way is to deal with this. So this is still ongoing research, basically to figure out how best to deal with these issues. Okay, that brings us to the end of this lecture. Thank you very much for paying attention. And if you have any questions, please post them on Moodle. Thanks.